Good morning. Good morning, everyone. Very glad to be here and to talk about observations of polluted white dwarfs. First, my name is Siyi, and I'm an astronomer at Gemini Observatory, which is a program under NOAA Lab. Yeah, so very glad to be here to talk about observation of polluted white dwarfs. Specifically, I want to focus on development for the past few years. I'm really excited because of different surveys and the things coming online. There are quite a lot of interesting discoveries. Start with, this is my cartoon illustration of white dwarf planetary systems. So good to be here that I don't need to explain what is a white dwarf. So in general, we think there are planets, debris belt made of dust and gas and the planetesimals around the white dwarfs. So just look at it, in my view, it's kind of pretty similar to the solar system, right? We have planets, we have asteroid belt, we have planetesimals, I mean like minor bodies like asteroids, comets, moons, like small objects. But you see the scale is quite different. Just in my mind, I feel that most of planets probably need to be a few AU away from the white dwarf. It's just because during the red giant stage, like a lot of the inner planets will be engulfed and destroyed. And then in terms of the planetesimal belt, in terms of the debris disk belt, we see quite a lot of them within the white dwarf's tidal radius. So it's about 100 white dwarf radii or 0.006 AU. So they are very, very close to the white dwarf. Yeah, and then when I first learned about this picture, it seems pretty strange, but actually now we've detected each single component of all these. I don't have time to talk about all of them, so in this talk I will focus on polluted white dwarfs. So what are polluted white dwarfs? These are basically white dwarfs that show elements heavier than helium in the atmosphere. We used to think they're very rare just because white dwarf has such high surface gravity, so things will settle out very quickly. But we now know they're actually pretty common, and most of them, they form because they are accreting from this planetary material like surrounding it. Therefore, by observing the polluted white dwarfs, we can figure out the chemical composition of the extrasolar planets. So another background, why it is so important, or why it is so hard to get exoplanet composition. So this is a mass radius diagram, which is used very commonly in exoplanet studies. This is a classical paper in 2007, but the basic idea is still pretty much the same. So basically for a planet, you measure the mass, you measure the radius, and then you kind of put it on this mass radius diagram, trying to figure out the composition. So in 2007, there's some, now the model is much better, but they consider some simple models. So this blue line is basically how a pure hydrogen like planet would look like in a mass radius relationship. And then this dotted line is a mix of hydrogen and helium. And you see like Jupiter is like here. So it works pretty well. And then like the other triangles are like Mars, Earth, they basically fall along different mass radius lines. So these days in exoplanet studies, people try very, very hard to get an accurate mass, get an accurate radius, and then you figure out the composition. But I think this problem is intrinsically difficult using this method because you have two observables, mass and radius, and you have a lot of free parameters, right? So that's why I think we're doing better, or we're doing a different way to look at this. Okay, so a little bit of history about the Van Manen star, and it's actually a prototype of polluted white dwarfs. So this is the Van Manen spectrum back in 1917, more than 100 years ago. And actually, when it was first observed, it was called Van Manen's F star. So because he thought he found it the faintest F star. And only later, based on parallax and the stuff, they realized, oh, it's actually a white dwarf. It's not an F star. And this is a modern presentation of this. So you see, it's a very heavily polluted white dwarf. It has calcium, magnesium, and iron. So in a way, we can say we actually already have the first evidence of exoplanet more than 100 years ago, but we didn't have this realization until fairly recently. Okay, so how exactly do we do that? It's actually pretty similar to the other studies. We use high-resolution spectroscopy. We observe heavily polluted white dwarfs and try to figure out the composition. So here's some representative spectra with KEK high-res. And then here I'm just showing like the calcium to hydrogen abundance. The top one is an upper limit, and the bottom ones are like detections. And just in comparison, the solar value is minus 5.7. So you can see this is an extremely sensitive method. We can detect very small amount of material just because the white dwarf's atmosphere is so pure, it's just so clean. And then if we also get a UV spectrum, we can get other kind of element, particularly volatiles, like in this case, sodium, in this case, nitrogen, and also sulfur and carbon and oxygen, like a lot of the volatile elements, and it's really only possible in the UV. So what have we found? So these, we've been working very hard, but these are like about the best studied systems we have to date. And I'm plotting them in terms of mass fraction of different elements. So I'm also showing Earth and comet Halley for comparison. So I'm plotting like oxygen, magnesium, silicon, iron, and then carbon. Because in comet Halley, there's quite a lot of carbon. So these are kind of two solar system objects for comparison. And all these, about 20 or so, polluted white dwarfs, that's what we have measured. So we see like they look pretty much like a solar system object. We didn't find any super exotic material. But if you look carefully enough, there are some differences. For example, some objects here, they have quite a lot of oxygen, and they have so much oxygen, almost too much oxygen, that we can't really combine with all these other normal elements. So we think they must have quite a lot of water. And then on this end, there are two objects that have quite a lot, or maybe three, have quite a lot of iron. So these more like, they're probably like mercury analog. They have accreted a lot of iron-rich material. And then I'm just saying we're slowly marching our way. We're moving away from astronomers' periodic table, which is hydrogen, helium, metal, to this. So actually, we have detected 24 different heavy elements in polluted white dwarf atmosphere. So, which I think is quite impressive, right? Given like such tiny bit of amount of material, we are already seeing them. And specifically, I want to highlight the 3 elements that were just detected last year. And I'll walk you through, because I feel every time we find a new element, we always learn something new about the physical process or about what's happening in those systems. So first is the beryllium. And it's detected in 2 white dwarfs. And you can see here there's a strong beryllium line here, which is around the 3130 angstrom. So it's really made possible by first the high beryllium abundance in this white dwarf, and also the high like blue UV sensitivity. And then if you look at the beryllium compared to other elements, so here it's showing silicon over iron, beryllium over iron. So these are the detection in these 2 white dwarfs, and these are like sun, Siyi chondrites, bulk Earth, like they're all basically clustered here. So it's like about a factor of 100 enhanced in these 2 polluted white dwarfs, which is kind of unexpected because it's pretty hard to produce beryllium. So there are different scenarios. The authors went through different scenarios, but in the end, they think the most likely case is actually spallation by either oxygen, carbon, or nitrogen in a very high energetic environment. So I think that tells us something really interesting about the formation when the planetesimal was formed. It must have gone through a very like active environment in order to have such high beryllium abundance. And then there's also detection of lithium and potassium. So so this is a lithium line, and this is a potassium line. So I think these are really made possible first by Gaia. Gaia finds a lot of cool white dwarfs and dedicated spectroscopic follow-ups. So so far, I think lithium has been detected almost a handful of objects, and they are all really cool, like 4,000 Kelvin. So these are very cool objects. The total age is probably 10 gig year, and the lithium is very much enhanced. So again, it's kind of puzzling because the standard Big Bang nucleosynthesis says lithium was only produced in the first 5 minutes. And afterward, all the other process pretty much destroys lithium. So how do you have so much lithium? So I think at least two theories out there. So one idea is precisely maybe we are actually probing Big Bang nucleosynthesis. So here, we are showing like age in the x-axis and the lithium over calcium in the y-axis. And these are the 2 objects with high lithium abundance. So the idea is precisely maybe we are sampling planetesimals that formed 10 gig years ago when there was more lithium in the universe. So this is just a natural effect of back then there are more lithium. And you can kind of see a trend about lithium decreasing. So if it works, then maybe we can use this system to probe the lithium abundance in the universe, kind of as a function of time. So that would be a pretty neat way. Another idea is, again, when you compare with solar system object, so here it's showing potassium over sodium and lithium over sodium. So these are the two different white dwarfs. And then you can see like lithium is very much enhanced, right? And all the solar system objects are here except continental crust, which is here. So an alternative explanation is maybe like these two white dwarfs are creating more like continental crust type material. That's why it's so enhanced in lithium. So I think the jury is still out there, and maybe there's a third explanation about why there's so much lithium in these systems. Okay, and then if you move beyond individual element, if you try to look the mineral type, so this is another way kind of to look at the accreted material. We use this kind of ternary diagram, which geologists use a lot. So the idea is basically trying to probe the relative fraction of three minerals. And you can see most solar system objects fall around here. And then the polluted white dwarfs are the diamond. And most of them also fall within this diagram. So it's kind of minerally, a lot of them look similar to solar system rock. However, you do find that quite a lot of them fall outside of the range, which means you cannot use this kind of ternary diagram to explain it. So we have to do other kind of projections using different minerals. And then by this presentation, we actually did not find much object look like continental crust. So continental crust is here, by the way. We find objects more like below here. So using this argument, it seems we are seeing more like mantle type material rather than continental crust. Okay, moving even further, when we look at an even bigger sample of material. So in this study, we've been focusing on cool white dwarfs. So it's with a cooling age between 1 and 8 gigayear. And in the y-axis, we are showing the accretion rate. So like the average mass accretion rate of those polluted white dwarfs. So and then all these objects have been updated with Gaia parallax and the white dwarf parameters. So what we find is kind of contrary to previous studies. Previously, we thought the accretion rates have like an exponential decay, which is this dashed line. Like so, but then like in this work, we seem to be seeing like during this 8 gigayear time, at most we are seeing a factor of 10 decrease. So which is this dashed line. So that shows whichever process is to make tidal disruption happen, it must be slow and steady, and it must be going on for quite some time. Okay, with that, that's kind of the summary of the first part of my talk. Hopefully, I've convinced you high-resolution spectroscopy of polluted white dwarfs is a very powerful way to measure the composition of extrasolar planets. I think we can learn a lot by studying individual systems, particularly with new detections of elements and understanding of the formation scenario. We can also learn a lot by looking at them as a sample and trying to find out the overall properties of these systems. And looking forward, I think there's still quite a lot of work to do. And particularly things I'm interested in learning more about is, first is really about understanding the systematic uncertainties. We heard quite a lot in this conference like earlier about how the white dwarf parameters don't always agree, how the atomic data is really, really important. And particularly when we talk to people not in the white dwarf field, how do they really understand our abundance and interpret the uncertainties? I think it's really important. And the second part is how does tidal disruption work? Like we find disintegrating bodies, we find circumstellar gas debris, like how does the tidal disruption process might change the composition? I think that's also really important. And the last bit is what really is a parent body? And are we seeing fragments of planets? Are we seeing asteroids? Are we seeing moons? I think that's also important to know, like what exactly we are looking at. All right. Move on. For the last bit of the talk, I do want to talk about planets around the white dwarfs, which I'm super excited about because I usually go to exoplanet conference. When I talk about polluted white dwarf, people ask me, have you found a planet yet? And now I can say like, yes, we find a few actually. And they all come like almost too quickly. So first one of its kind is actually an evaporating Neptune-like planet discovered by Boris and the team here. So what exactly they have seen is this is a polluted white dwarf, but it's very volatile rich. And contrary to previous observations, they didn't find the calcium, they didn't find the iron, they didn't find all the normal rocky material. What they find is all the volatile things such as sulfur and oxygen and H-alpha. And then they find the volatile rich material both in the polluted atmosphere and the circumstellar gas. And then after going through a lot of scenarios, in the end, they conclude the most likely scenario is it's probably an evaporating Neptune-like planet. And also the white dwarf is really hot, 28,000 Kelvin. So basically because of the strong radiation, the Neptune-like planet is losing its atmosphere. And that's how we are seeing it. All right, and then there's also TESS also find a transiting planet candidate around the white dwarf. So here are how the light curve look like. First is from TESS, then from different ground-based observations, and then also with Spitzer. So the good thing is the light curve looks consistent. It's not changing. Thank God there's an intact planet. It's not disintegrating. And then like the shape and everything, they all agree. And then we get the parameter. It's actually a very old white dwarf. It's DA. It's about 5,000 Kelvin, like log G also is pretty normal. And the period is only 1.4 days, which means the semi-major axis is 0.02 AU. To me, it just blows my mind. It's quite different from the cartoon diagram that I thought of earlier. And then from the light curve, we know it's a Jupiter-sized planet, but it's actually pretty hard to get a mass. If you're interested, I can tell you more about why it's difficult. But anyway, we think the mass is 0.8 to 14 Jupiter mass, so it's really unconstrained. That's why we still call it a planet candidate, because technically, if it's 14 Jupiter mass, it could be a brown dwarf. So, and then the equilibrium temperature is 163 Kelvin, which is only a little bit warmer than Jupiter. So it's among the coolest transiting exoplanets known. And how this object got there is really still a big puzzle. Maybe it survived through common envelope phase under a set of very lucky conditions, or maybe somehow it would get there like after the star become a white dwarf. And then the same year, there's also a very interesting Jovian analog around the white dwarf using gravitational microlesning. So I just want to admire this light curve. Look how different it is. Like totally different from the transiting light curve we're seeing. And then what the microlensing people do, I guess, is when they find this signal, right? They just wait. They wait until the source and the lens moved away, and they try to figure out what kind of transit that actually is. So this is what they did. They did a very high contrast imaging. This is in 2015, 2018. So this bright object is the background source object. And then they are trying to detect the lens object, which is a star plus a planet. But actually, they didn't find anything. So this is the background object that's unrelated. And then according to this is the contour plot about the most likely position of the lens object. And based on this non-detection, they conclude that the most likely host is actually a white dwarf. And then it's a 1.4 Jupiter mass planet with a projected separation about 3 AU. So in a way, this object is where I expect the planet to be. And actually, the authors say, because a few AU is microlensing most sensitive to, so the fact they detected one might mean there are quite a lot of objects like at this separation. There are quite a few planets around this separation around white dwarfs. So I'm really interested to learn a bit more to see if they find more such systems. Okay, so summary of this part of the talk, and I just think it's amazing there are such diverse methods to detect planets around the white dwarfs. There are at least 3, and they use 3 very different methods, right? Spectroscopy, transit, microlensing. There's also this astrometric planet candidate. And then we also learned about Keaton's disappearing white dwarf survey. And then there's another talk in this session talk about a possible planet candidate. So I think all this is really coming together. Yeah, but there's still quite a lot of questions like, really, how did the planet get there? Now we finally find the planet. It'll be good to know how it actually got there. And also, how does the planet and the pollution go together? Because before I would have thought if there are the planets, there must be pollution, but it doesn't seem to be always the case. So I think we need to understand what exactly is happening there. And lastly, just a little advertisement. This is, we wrote a code, which is a Python package to derive Bayesian ages of white dwarfs. Rocio Kuhlman is here, and we thought it's a nice tool for the community. So please talk to her, and yeah, that's all. Thank you, and I'm happy to take any questions.
Questions? Keaton?
Great talk. I often see the same figure quoted in papers all the time from Kester et al. 2014, that's like the occurrence rate of pollution is between 25% and 50%. Right? Do we have a better handle on that, like in terms of precision by now?
So the question is asking the occurrence rate of pollution, right? I think it's hard because you need a really big sample. So like you need to observe a lot of them to get a proper, Boris might have an updated number. Okay.
Yeah, comment.
Yeah, just a quick comment. Metals detected in kind of 50%, but it's not clear what it means because radiator levitation at higher temperatures can just keep metals up. So it's how you interpret what you see.
Right, so just on that, that's why in Castor's sample paper is 25 to 50, right? It's 25 the lower bound, and consider like basically how much you incorporate radiative levitation, and the 50 if you consider like all detections is all from accretion. That's why it's 50. I think that's still the best number out in the literature. And of course, there's been study about in wide binary systems, would it be different, right? So the number is rather limited, but we seem to find if the white dwarf has a wide binary companion, depending on the separation, the occurrence rate might be a little bit different. So if you have a close binary, then close wide binary, then the percentage seems a little bit lower. But if you have a really wide binary, and then it's like more or less the same as single object. But Ben Zuckerman is here, and you can talk to him about this.
So is it surprising that the accretion rate doesn't go down very fast? Because if you look at dynamical simulations, I think people mostly say, you know, these tidal disruptions occur in the first giga year or so, but that's not what you're seeing. So what does that mean?
I know. I don't know what that means. I think, well, I think for one thing is we do need to figure out, do we agree on the accretion rate is not changing that much? I think some people in the audience do not think they are quite buying that result. And then second, if we do find accretion rate is mostly constant or only decreased a little bit, I think it really have very strong constraint on the dynamical models. And I think Chris might have a comment there about what that means.
Yeah, just to follow on that, it really depends a lot on which dynamical scenarios you're considering. So if you have planet-planet scattering intruding on planetesimal belts, then yes, you do see very rapid depletion of that reservoir and a very rapidly dropping accretion rate. But if you consider somewhat gentler mechanisms like some sort of secular driving from a more distant companion, then you can really extend things quite a lot.
Yeah.
Thanks, Siyi. This was a fantastic overview. Do you think the simultaneous accretion of multiple planetesimals could explain some of the weirder abundances and minerals we're observing?
Yeah, I think definitely. So the question is, are we sure we are creating one body, not like several bodies? And I think this is really, it is a possibility. Like we're not just seeing one object, we are seeing multiple objects. And actually there are a few systems which we think we must need that. Otherwise, like the composition is too hard to explain. Yeah.
Along those lines, there's just been a paper posted on AstroPH within the last week or two by Ted Johnson and colleagues, where a fairly hot white dwarf in the ground, 20,000 degrees. The argument is accreted two objects. One, or is in the presence, is presently accreting material from two parent objects, one that was core rich and had iron in it, and the other looks more like a Kuiper belt object and has volatiles in it. So one object came from far out and the other one much closer in, like in the asteroid belt or where the typical planets are. So anyway, that's a paper that's just by Ted Johnson. It just appeared on AstroPH in the last week or two.
Other questions?
So since this issue of accretion rate and thermohaline mixing came up, I was wondering if you could show the plot of accretion rate. I was curious about your and Evan's opinions about how much thermohaline mixing might increase the inferred accretion rates.
So you're talking about this one?
Yeah.
Okay, so as far as I know, thermohaline really only affect the hotter DAs. And so here we are looking at much cooler objects, like below 10,000 Kelvin. So I don't think it affects much. Did I get it right?
Evan, want to comment?
Yeah. Did I get it right?
Yeah, I mean, I agree. I think it's within about the first giga year, kind of matching up some with that dynamical prediction, but it would, it'd go several orders of magnitude higher than this this y-axis, but also I guess it would go, up and to the left from where this plot is showing things.
Right. So in that sense, I do think there's like, if we plot even hotter ones, there is a decrease there. So I think what we are arguing here is between 1 and 8 gig year, there doesn't seem to be much decay. So there is a decay here, basically. Yeah.
Other questions? JJ?
Hunter from the other side of the room now. So we have Gaia, we have lots of new white dwarfs, but it's very hard to get the types of observations we need to make that bar chart you had with that lovely review with Amy that you wrote last year. So how limited are we by ground-based optical spectrograph competition? How much of this do we need Hubble data? Like sort of what's the biggest bottleneck in expanding that sample, do you think?
Oh, there's so many bottlenecks. Great question. So I think JJ's question is, what are the bottlenecks and how can we get more of those objects, right? I think there are different approaches about how to do this. And so I don't know if they're the best approach, but my personal approach is I have been trying to look for white dwarfs with infrared access, because these are the ones with a dust disk, and these are the ones among the highest accretion rate. And then once I find those, I try to follow them up spectroscopically and trying to get the composition. And then usually you need the ground-based work first, right, to prove they are polluted, and then you ask for Hubble time. So that's my approach. But I think other people might have different approach. For example, they might focus more on DBs, the helium-dominated white dwarf, because in general, you just get more heavy elements from those objects anyway. And then biggest bottleneck, maybe manpower. We need more people. Yeah.
More questions? Go ahead.
I have a question, maybe a very naive question. There are some infrared or radar surveys like VVV, VISTA. I'm not familiar with how deep these surveys are, but since you are looking for red access, have you looked at those? Or are they useful?
Right. So the question is, in terms of looking for infrared access around the white dwarfs, are these infrared surveys useful? From my experience, I think like VVV, UKIT, those surveys are helpful in figuring out the field to see like if the white dwarf is an isolated source or if there are background contamination. But then I guess I didn't talk much about infrared access, but most of them really only show beyond the 3 micron. So you need a WISE, you need a Spitzer, and maybe you need JWST. Yeah.
We have time for another quick one if there's any. If not, let's thank Siyi again.
Thank you.